I figured if I wrote a word on the board that everyone would get really scared, so it totally happened. That's perfect. So that's how that works. So we're going to talk about minimum spanning trees today. Yeah, so we're just going to talk about graphs and how we might build connections on graphs. And it's mostly review. I think you guys have covered this ostensibly before. Have you guys covered this before? Yeah. So we're going to talk about, just to get started, yeah, the idea, do you guys know what you guys want to know what a spanning tree is? Okay. So yeah, let's set up some notations. So the idea is you have some input. You have a graph with some vertices and edges, such that your vertices in general, I'm going to start using like sequence notation sometimes because it just makes things more succinct. Have you guys seen this before? It's way smaller, so it just makes life a lot easier. It's the same thing. All it means is we're counting through all the elements indexed by I from 1 to n. So sometimes that's just way better than doing this all the time. If it drives you crazy or you get confused by anything, just let me know. So following that logic, these set of edges can similarly be some j's maybe to m. Yeah, it's much easier. Same idea. So this is the input for the set, and we have a goal. Actually, we also have some weights. In the set of real numbers. Also, we have the weights for edges. I could also be a little bit more clear, I guess. Just saying, like, I'm just setting up some notation so we can talk about both the edges between points and edges. Obviously, each edge is defined by a pair. Like, they're not ordered, they're not usually ordered, but in this case, they're not ordered. But it's good to set it up so that they can be either way. Does that make sense? Yeah? Okay, cool. So we have a goal. So our input is this. And broadly speaking, the goal is the output. Some subset of the edges, such that we minimize the cost function. And the cost function might be defined by some Does that make sense? Stop me if you want clarification. So the general idea is use some graph. It's defined by these vertices. Maybe I could make a little picture for you guys. Actually, that is.
Did you just write the minimum part of the spanning tree?
Yeah, we're trying to minimize the cost. So the idea is like this would be
That's the minimum.
the minimum that contains, and I guess there's a condition here, is that the edges span the whole graph.
Yeah, the metal beam is saying.
Yeah, so the condition is, T connect all the vertices in V vertices to say R I. Am I missing anything else? I think that's,
Trees have been scattered.
yeah, that's taken care of by the minimum cost, because you can't, yeah. Okay. So, there are some terms here that will clarify. In general, the costs in these problems a lot of times are positive. When you have negative costs, some of these definitions become a bit more rigorous. But I'm not going to bog the conversation down with that. And I think you guys have covered this stuff before. But let's set up some terms. So really what we're talking about is, I'll write it here under the light. Spanning tree. Which is acyclic. Connected. Subset of edges. So being a little bit redundant there, but that's okay. The acyclic part just means that there's no cycles. So if you want to draw some pictures in your notes, I'll assist you in that. And that there's a path between the fact that it's connected. There's a path between all vertices. Something like this might work, which is also a dog. Sorry. Okay. So there's some basic properties for all spanning trees. Turns out that the size of set T, the edges, is n minus 1, which if you recall is the number of vertices. It also turns out that, so this is like 0.1, it also turns out that removing an edge creates two graphs. So it disconnects the trees. When you limit yourself to the existing vertices, if you add any edge, it creates a cycle. Yeah, adding an edge obviously means an edge that's not already present in the graph. So, I think that should be sufficient. Yeah, okay. Sometimes I'm a little too rigorous in my notes and I say things that are pretty obvious. That's kind of our preliminary definitions that we can get out of the way. So now we can just talk sensibly about things and we have notation to do it. So that's all, I'm just throwing that at you guys. Don't forget to find a group. I mean, erase this, but doesn't mean you shouldn't find a group. If you want to go it alone, you can, but if you have a hard time, it's nice to have people to rely on. All right. Any questions with definitions or notation or anything like that? Or if I'm not infallible, so if I made a mistake or anything like that, you can let me know. Sweet. Okay, so what's the best way to go about this sort of thing? Like if you wanted to find a tree like that, if you have a collection of nodes, does anybody have any preliminary ideas? It's pretty simple. Wow. Sorry? Yeah, exactly. Like get Prim's algorithm, that's one way. Ostensibly, the algorithms either worry about the vertices or the edges, or both in some combination. That's the only options you have. So there's, you either try to select one or the other. So we're going to sort of compare some approaches. There's also the obvious approach, which is just, you can do brute force. That's always an option, given a graph. And if you want the optimal solution to some sort of problem involving an MST, it might be like a traveling salesperson style problem, but you need to find the absolute best choice. You can always rely on brute force. What we're going to do here is we're just going to kind of make a matrix of solutions. So I'm imagining that this would fit nicely in your notebook. And I'll try not to have the worst writing ever. So the idea for these give your brute force. As mentioned, we might be able to use something, maybe use Prim's algorithm. Turns out that that's around theta m log n. Yeah. So the general idea with Prim's algorithm is that if we have a graph, basically if we have a graph, we want to keep adding the closest next item as we traverse through the graph. That's the general idea. So yeah, so given some start point Ri, we want to add an edge EJ such that the weight Ri, Rk is minimized. And then, you know, as an aside, we just note that so we have to be careful though, because as we add a node, we want to make sure not to add a node that's previously been added or create cycles. So we have to be careful of cycles. As a contrast to focusing on specifically on the upcoming nodes, we could also choose to focus on the set of edges instead. So it's just a different idea, and it can be beneficial. And so it turns out, I feel like this is what I wrote down. So. Yeah, so the idea is to keep adding EJs that are not already in the set that you're building, such that is the minimum. Yeah, so it says the minimum weight that doesn't. So in both the cases, we have to be careful not to redundantly add edges or nodes that create cycles. And that's a general rule with these algorithms is finding ways, as you're traversing through this set of nodes or edges, that you make sure to guard against adding duplicates. Yeah. And so with Kruskal's, there's kind of for the complexity, there's a couple things going on. Specifically, the first thing that happens with the algorithm is that you sort the edges. And so that can happen in and then you have to enter some sort of a main loop, and you might do sort of a union or a find set operation there. And that happens in, so this is your loop. And this is your exploring the graph. So just throwing that stuff up, we're gonna sort of go through the algorithms a bit as a refresher. But does that sort of make sense at the outset? Does everyone have the notation now? I think so by now. Because we're going to expand what we're doing there with the idea. So, yeah. Okay, so let's talk about runtime a little more specifically for all these guys. Not straight at all. Okay, so for prims, like we said, it's around theta m log n, and the general idea is that we use a min heap. To create priority queue. For Kruskal's, oh, I kind of got this messed up. There's an empty space there. I have an idea though. So brute force is, you know, and for Kruskal's, I sort of went over it. But yeah, the first thing that happens is sort all of the edges. And then enter your main loop. And it turns out that the sort of the best way to do that is yeah, okay, cool. And there is one more I want to mention, and I'll throw it at the bottom. And it's the reverse delete, which is you start with a full graph, and then you start deleting elements until you get down to a minimum tree. And it's a little bit more complex, just by virtue of the fact that you're starting with such a big set of data. So the general idea, so this is on the order of the amount of edges squared. And the idea is that for all the edges j, basically that. I don't want to go into too much detail about the reverse delete, so just because it's not super good, but you can definitely look it up. So given all of that information explosion, so this lines up about here. If that makes sense. Yeah, that's about right-ish. Yeah. I wish I could do cut and paste and move things down on chalkboard, but that's not how it works. So that was an information explosion. So we set up some notation. Now that we have notation, we've set up a few solution approaches: Prim's algorithm, Kruskal's algorithm, and the reverse delete. And now I'd just like to show you guys a little bit of how Prim's algorithm actually and Kruskal's actually operates, to sort of clarify that. And then we'll get into talking about how we might show that these algorithms actually work, if they function or not, and if it, build the MSTs that we expect. Is it clear what we're doing? Like, is it a little too mathy and not enough example? Is it clear we're exploring a graph and trying to build a spanning tree of that and what that looks like? Yeah. Okay. Cool. So let's construct a basic graph. With some candidate edges. Oh. So, given the graph here, and some initial sets, does anybody want to walk me through prims? Given some sort of, yeah, starting vertex A. And helps if you have labels, right? Two E's, so I'll say D, E. So what's the first choice for the algorithm? So the idea is that we want to build a minimum spanning tree. We're given this initial starting point A, and the goal of Prim's algorithm is to add the next closest item, next closest edge, or sorry, edge and also vertex. So,
Do we have 7 or 6 edges?
1, 2, 3, 4, 5, 6 edges. Yeah. Yeah, 6 edges. Thanks. So, starting at A, the easiest connection to make, oops, is AB.